All right, welcome back to class. So we're getting pretty complicated in our abilities to identify the empirical formula for a compound given just the mass of the different elements, right? So, for example, last time we could identify that the chemical formula for this compound was CHCl simply by being told the percentage of the different elements. And remember, this is the mass percentage of these different elements in the compound. All we had to do was assume we had 100 grams of this material and then say, okay, if I had 24.77 grams of carbon, how many moles of carbon would that be? If I had 2.07 grams of hydrogen, how many moles? And so forth. And then when we knew the moles, we could simplify those values to whole numbers and then find out the empirical formula. And then, after we had the empirical formula, if we were given molar mass information, we could compare the empirical formula's mass, the empirical mass, to the molar mass, the molecular mass, and that the difference there, or the multiplier between those two, would also be the multiplier on the number of atoms in the molecular formula. All right. So now we're going to introduce a new wrinkle. We're going to show you how somebody learns how much carbon there is in a given compound. So we talked about the President of the United States getting a mysterious white powder on his envelope, and we have to figure out what that white powder is to see if it's poison or not, right? Well, how would we determine what the empirical formula for that compound would be? We'd have to find out how much carbon, how much hydrogen, how much oxygen, nitrogen, and whatever else is in there. And this is how that happens. We put our material, right here represented by this little black pile of material, into a tube that has oxygen flowing through it in this direction. So the oxygen goes in this way, and it can travel through this absorbent material, and then it can travel through this absorbent material, and then it travels out the end there. Okay? So what's happening is our compound, which we have to assume has some carbon, some hydrogen, we'll put X on there and Y on there, is combining with oxygen gas because we're putting oxygen gas in here and we're heating it, we're burning it, we're getting it really hot. And that's what happens to things that have carbon and hydrogen in them. When you burn them or when you heat them really hot in the presence of oxygen, that's what we call burning, right? And you remember on a campfire, you put a piece of paper on the heat in the presence of the oxygen, burns it. What happens to a campfire if it doesn't get enough oxygen? Do you know?
It dies down and it dies.
That's right, it dies down. It won't burn. It'll just kind of sit there and smolder very slowly because it's limited by how much oxygen is getting into the fire. So if you give it lots of oxygen and plenty of heat, then this reaction will produce carbon dioxide and water. So the carbon that was in this compound here combines with the oxygen to form carbon dioxide. The hydrogen that's in the compound combines with the oxygen to form water. Okay? Well, these carbon dioxide is a gas. Water can be a liquid, but because of the heat that we're providing, it comes out as a gas as well. So the burning occurs, and then the products, the carbon dioxide and the water, are flowed through these, what we call U-tubes. Did you know chemists invented U-tubes? See, there they are. They had U-tubes a long time ago. The carbon dioxide and water goes through the U-tubes. This one absorbs all the water, and this one absorbs all the carbon dioxide. And so you look at the mass of this U-tube. You can see you can disconnect it right there and put it on the scale. Find out how much it weighs before and after, and it'll tell you the grams of water that you got from that elemental analysis. And then you can do the same thing with this U-tube over here, and it'll tell you the grams of carbon dioxide that came off of this process. Okay? You can also do very similar type of thing nowadays and find out different amounts of not just carbon and oxygen, not just carbon dioxide and water, but also other elements. Okay? So, we call this a combustion analysis. Combustion is any time we react something that has carbon and hydrogen with oxygen, because the products of combustion are always carbon dioxide and water, right? You burn your paper on the fire and the result is carbon dioxide and water. If my body, uses sugar, I eat the sugar, I breathe the oxygen, it produces carbon dioxide, that's what I'm breathing out, and water. When you breathe out on your hand, you can feel it's wet because I'm breathing out water, okay? So I burn sugar and oxygen in my body, or if I burn it in a can, wherever, the products will be carbon dioxide and water. Now, from the amount of carbon dioxide that I get out, I can determine how many moles of carbon I started with. And from the amount of water that comes out, I can determine the moles of hydrogen. And from the moles of carbon and moles of hydrogen, I can get the empirical formula. Okay? So we're going to look at that. Here's an example. If I have a sample of material, this is my sample of material here, 5.217 grams, 5.217 grams of material. And then I burn it, I combust it. Combust is another fancy word for combining with oxygen to form carbon dioxide and water. I get 7.406 grams of carbon dioxide and 4.512 grams of water, and from that we want to calculate the empirical formula. We want to calculate the empirical formula. Okay? Well, again, I'm going to write up here C, X, H, Y. Now, there is also some oxygen in there, and we'll talk about how we can determine the oxygen in a bit. But see, the amount of carbon here, X represents, again, the moles of carbon. Y is the moles of hydrogen, and Z is the moles of oxygen. So the first thing I want to solve for is the moles of carbon, right? Moles of carbon. And what I have to start with, this time I don't have grams of carbon, but I have grams of what that contains the carbon?
Carbon dioxide.
That's right. So I can go 7.406 grams of carbon dioxide. All right. Now what goes down here?
Carbon dioxide.
And what are the units for the carbon dioxide?
Grams.
Grams, that's right. And I can convert those grams to, we always like to go to the land of the moles, because in the land of the moles, we can get the stoichiometric relationship, or the power of this ratio, which is X to Y ratio, right? So if I go from grams to moles of carbon dioxide, then from moles of carbon dioxide, I can go to moles of carbon, because I can see how many moles of carbon, and that's what I want, are in every mole of carbon dioxide. How many moles of carbon are in 1 mole of carbon dioxide? Can you tell?
44.
Well, that's how many grams, that's good. That's how many grams are in 1 mole of carbon dioxide. Very good. Now what about this one? How many moles of carbon are in a mole of carbon dioxide?
1.
1. That's right. 1 mole of carbon for every 1 mole of carbon dioxide. Very good. So, the fan is too loud. So, I can solve this. Can you put your calculator to work and find out how many moles of carbon there must have been in the initial sample if I got 7.406 grams of carbon dioxide?
Is it 0.168?
Yes.
3?
Very good. That's exactly right. That's how many moles of carbon. Very good. Now, let's do the same thing, but this time we're going to get moles of, we already got moles of carbon here, right? What do we need to get now?
Oxygen.
Well, let's do hydrogen first. All right? Moles of hydrogen. What am I going to start with that's going to help me with moles of hydrogen?
Oh wait. H2O.
That's right.
Grams of H2O.
Grams of H2O. And I got 4.512. 4.512. So how many grams of water are in 1 mole of water?
There is 2 and 18.
Very good. 18 grams for every mole of water. And then, if I have 1 mole of water, how many moles of hydrogen are in 1 mole of water?
2.
2. Very good. So we got 4.512 divided by 18 times 2, and that'll give me my moles of water. Can you figure that out on your calculator?
Yeah. Point 5013.
What'd you get?
0.5013.
5013. Okay, very good. So, from this now, I have the moles of hydrogen and the moles of carbon. So I am getting really close. I got C 0.1683, H 0.5013, and now the last one I need is the O, the oxygen. Now the chemical reaction again is this. My carbon and hydrogen, and in this case I have some oxygen on my compound, right, is combining with the oxygen to form carbon dioxide and water. But I don't know if the oxygen on this compound ended up on the carbon dioxide or on the water, because the oxygen is also ending up on the oxygen or on the carbon dioxide and water. This oxygen and the oxygen in my compound. So I can't tell simply by looking at the grams of these two. But what I can do is I can find out the total mass of this material, which is the 5.217. And now I know the total moles in that sample and the total moles of hydrogen. And from that 5.217 grams of sample, I can subtract the grams of carbon and I can subtract the grams of hydrogen. And if I do that, what should be left over?
There is how much?
Well,
Hydrogen?
I mean, if I have a sample that contains carbon, hydrogen, and oxygen, and it has a total mass of 5.217. And if from that total mass I subtract my grams of carbon and my grams of hydrogen, all that's going to be left over is the grams of oxygen. Can you see that?
Yeah, but I don't know how much grams of
Carbon?
carbon there is.
Yeah, we don't know how many grams of carbon, we don't know how many grams of hydrogen. But we do know moles of carbon and moles of hydrogen, because we just found that out. It's 0.5013 moles of hydrogen, and it's 0.1683 moles of carbon, right? So how can I find out how many grams of carbon 0.1683 moles of carbon is?
You put moles of carbon bottom right,
Very good.
and then top right you put grams of carbon.
Okay, so what numbers go in there?
1 mole of carbon equals 12 grams of
Carbon. Very good. So, calculator, 12 times 0.1683, right?
right.
So that's 2.0196. 2.0196, and that's grams of carbon. So I can put this value in here, 2.0196. Very good. How many grams of hydrogen?
Put moles of hydrogen bottom right,
Mm-hmm.
and then top right 1 gram of hydrogen.
Very good. So it's just the 0.5013, huh?
Yeah.
It's the same, huh? Because I just multiply by 1 and divide by 1. All right. Can you tell me how many grams of oxygen there must have been in that sample then? Can you get your calculator out and tell me that?
One second. It
Okay.
said air. So I'm gonna
All right.
try it different.
All right, did you get it?
Yeah.
What'd you get?
2.9691.
2 point what? 69? Or no?
69.
69?
2.961.
2.6961?
Yeah.
Okay. All right, great. Now, can I put that 2.6961? 2.6961 grams of oxygen. Can I put that right here?
Yeah.
Well, is this grams of oxygen down here? Is this grams of carbon, grams of hydrogen?
No, it's moles.
It's moles. So what do I have to do with that grams of oxygen?
Turn it into moles of oxygen.
That's right. Moles of oxygen. Grams of oxygen, moles of oxygen. On the periodic table, it's what? How many?
16.
16 grams per mole. So I take my 2.6961 and divide it by the 16, and then I get 0.1685. 0.1685. All right, now how do I get this into a whole number?
Divide it by the smallest number.
Which one's the smallest number?
1683, 168.
Hmm?
5? That is 7 or a 5?
This is a 3 and that's a 5.
Okay. Then it's divide them all by 1. Wait. Yeah, by 1.683.
Yeah, by 0.1683, right? So I know that this one here is going to be 1, carbon is going to be 1, and the oxygen is going to be close enough to 1 too, right? So the hydrogen is the only one that I really have to do. So if I do 0.5013 and divide it by 0.1683, I get 2.97, which is pretty close to what?
3.
3, yeah. So my empirical formula is C H3O. Very good. CH3O. So again, I use the carbon dioxide to get to moles of carbon and then to grams of carbon. Water to get to moles of water and then grams of water. Subtracted my grams of carbon and grams of hydrogen from my grams of sample to get grams of oxygen, and that grams of oxygen led me to moles of oxygen. Okay, very good. Here's another one. Combustion analysis of 3.88 grams of a compound containing carbon, hydrogen, and sulfur reveal the following data. And we want to know what the empirical formula is. Okay? So, why don't you start working this on your screen?
Okay.
All right, so we got our empirical formula. It's like going to be CXHYSZ. We got 3.88 grams of this stuff, and we burnt it, and then we got 9.377 grams of carbon dioxide and 1.59 grams of water. So, how do we find out first the moles of carbon dioxide? Or sorry, moles of carbon.
So we're trying to figure out how many moles of carbon there is?
Yeah, well, we want to know moles of carbon, moles of hydrogen, and moles of sulfur, because that's what the empirical formula is, right? CXHYSZ, that X, Y, and Z are the moles of the different material in that compound in a given amount. So, equal sign, moles of carbon, right?
Why is there an S?
Because there's sulfur in this compound. This compound, they didn't have carbon, hydrogen, and oxygen. This time they had carbon, hydrogen, and sulfur. But we can solve it the same way by finding out how many grams of carbon and grams of hydrogen there are at some point, and then subtracting that from the grams of total. And that'll give us grams of sulfur, which we can convert to moles of carbon. So tell me what you're doing there.
I'm writing carbon dioxide.
Good. Grams of carbon dioxide. 9.377 grams. Excellent. And then you're going from grams of carbon dioxide to what? Moles of carbon dioxide. Very good. We want moles of what? Carbon. Very good. Moles of carbon. So then we're going to go from moles of carbon dioxide. Are you going to write that in first? Okay. Moles of carbon dioxide. To moles of carbon. Very good. And that's an easy 1-to-1 ratio. Very good. And this one is 44 grams per mole. And we got that by adding 1 carbon and 2 oxygen masses from the periodic table. Very good. So I'll do the calculator, okay?
Okay.
We got 9.377 divided by 44. That's 0.213. 0.213. 213. So no 1 in there, just the 0.213. Very good, 0.213. Great, now let's do moles of hydrogen. Very good. We're going to find moles of hydrogen. And we're going to start with what? .59 grams of the water. Very good. We have grams of water down there. Excellent. Moles of water up there. Does that say 32? What does that say? Are you changing it? What did you change it to? 18. Very good. 1 oxygen, that's 16, and 2 hydrogens, 1 and 1, so that's 18. Very good. Now, how do we get to moles of hydrogen? Moles of water. Very good. Moles of hydrogen. 2. Very good. 2 moles of hydrogen for every mole of water. I'll do the calculator again. 1.59 divided by the 18 times 2, that is 0.176. Very good. Okay, now let's go to what's next? What are we supposed to do now? How do we get, we got moles of carbon and we got moles of hydrogen. How do we get moles of sulfur?
Do 0.176 times plus 1 times 1.
What do you mean? What we have to do now is we need to take the mass of the sample, 3.88, that's the grams total, and we need to subtract the grams of carbon and the grams of hydrogen, right?
Right.
So how do we determine how many grams of hydrogen? We got moles of hydrogen. How do we determine how many grams of hydrogen? Or is it the same amount because it's a 1-to-1 ratio?
Add 1 gram?
No, we convert the moles of carbon. So
1.176 divided by 1?
Yep, that's right.
I
But
did that in my calculator.
Yeah, okay, that's 0.176, right? Grams of hydrogen, right? Very good. Now we also have to subtract grams of carbon, right? Good. Good. So how many grams of carbon? How do we find out how many grams of carbon?
0.213 divided by 12.
Why don't you write the equal sign and then use that moles of carbon that you have right there and convert it to grams of carbon?
What?
Why don't you set up that equal sign, put the equal sign down there. Why don't you go back to my thing real quick, my screen real quick. So you got 0.217 moles of carbon. And we're trying to think, do we divide it by 12 or multiply by 12? Well, if you put grams of carbon here, then you see what has to happen. Moles of carbon, grams of carbon. 1 mole is 12 grams. So I see that I need to multiply it, right?
Right.
Okay, so make sure you use your tool there. Always use the tool so that it can tell you what you need to do, because it's just clear when you use the tool. If you don't, you might be guessing and you might not be right, and then you just move forward because you don't know that. So go back to your screen now and we'll watch you do it.
So I do. Wait, so I do what you did just now?
Mm-hmm. Very good. Moles of carbon. Outstanding. And then moles of carbon there. And then we go to grams of carbon, right? Very good. So 0.213 times 12. That is equal to 2.556. So if I take 3.8 and subtract 2.556 and then subtract 0.176, I get 1.148. So the answer is 1.148. 1.148. Very good. Grams of what? What is it? Of sulfur. Very good. Now, can I use that 1.148 on my Z?
Yes.
Oh, be careful. That Z is not supposed to be grams. It's supposed to be what?
Moles.
Yeah. So on the very bottom of the page, convert that grams to moles. Moles of sulfur over there. Good. Good. 1.148 grams of sulfur. Grams of sulfur. Moles of sulfur. What's the periodic table say? It's number 16, element 16, 32. Very good. 32 grams of sulfur for every mole of sulfur. So if I take the 1.148 and divide by the 32, then I get 0.0359. 0.0359. Very good. 0.213. 0.176 for the hydrogen. And then the sulfur is 0.0359. So, 0.0359. No 1 in there, just 0.0359. Very good. Excellent. So what do we divide them all by?
2.176.
No, isn't the 0.0359 the smallest?
Oh yeah, 0.0359 is the
Yeah, 0.0359. So I'm going to copy down what you have, and so you can turn back to my screen. C 0.213, H 0.176, S 0.0359. All right, turn back to my screen now. So now I divide all of these by You ready?
Yeah.
Okay, so I divide them all by what?
You divide them all by 0.0359.
Very good. .213 divided by 0.0359. That's 5.9. That's pretty close to 6. 0.176 divided by 0.359. 0.0359. 4.9, that's close to 5. And then the last one is going to be 1, right?
Yeah.
All right, is that one of our answers?
No.
It's not?
Oh wait, it's A.
It's A! Hooray! We got it. We got the answer. That's a lot of work. Fabulous job. But isn't that a powerful thing? You can burn the material, find out how much carbon and oxygen, hydrogen, or carbon dioxide and water came off, and then you can find out the empirical formula from that. Good job for today. Thank you.